Okay, so in this video I'm going to run through some stuff on rates just to help you revise it, and then you can crack on and do the exam questions yourself. I've got a reaction here. I've written it at the top, but you're given the info in the question, and the first thing they want to know is how you can measure the rate. So the fact that hydrogen is a gas is significant. You're going to use that. You are going to capture the gas in a gas syringe and measure the volume produced over time. Okay, when we're talking about rate, we need to remember that rate is a speed, and if I ask you for the speed of a car, it's in miles per hour or kilometers per hour, or you could talk about someone running in meters per second. But to give information about speed, you need to reference time, and if you just collected the hydrogen in a volume or in a gas syringe, at the end you know how much hydrogen you had, but you'd have no idea how quickly that hydrogen was formed, so you wouldn't be able to give your answer as a speed. So just make sure you're measuring time. Measure the volume of the gas produced over time. I'm using a gas syringe, I'm using a stopwatch. Your other option here would be to let the hydrogen gas escape and measure the change in mass. However, when the gas is hydrogen, that's actually quite difficult to do. Hydrogen is really light. Remember, it's got atomic mass of just 1, so the entire formula mass of hydrogen is 2. And even if you were to release a number of moles, the mass released is still going to be very small, and you need a very sensitive mass balance to be able to detect that change in mass. So when your gas is super light, like hydrogen would be, the gas syringe is a much better choice of method. The mass balance wouldn't be able to detect the loss in mass of just losing hydrogen. The rest of the questions relate to collision theory, which I know you probably think that you know, but I think there's a few things in here that might catch you out. So the first one is explain the effect if you're using 0.2 mole per decimeters cubed. Okay, first of all, we need to spot that is a concentration. Moles per decimeters cubed is the number of moles dissolved in a given volume. That is a concentration. And I'm going from 0.1 to 0.2, therefore I'm increasing the concentration. So the equivalent to this is if I said there is 60 people in M32 instead of 30, are you more likely to collide? The answer is yes, therefore the rate increases. Alright, so you're going to say the rate increases because you've got more frequent collisions. That abbreviation will not work in your exam, FYI. More frequent collisions, and the reason you've got more particles per unit volume. You have to specify that the volumes change, the volume's staying the same, but you've got more particles in there. If you were to draw this on a graph, okay, that's my original line. Because the rate has increased, I'm drawing it steeper, but because I've got more particles, because you're starting with more reactants, you will make more products, and that's why I can go higher on the y-axis. Now the next one, explain the effect if you're using 200 centimeters cubed. Now initially it was 100, now it's 200. You have increased the volume. Okay, now this is the equivalent of me saying, all right, I'm going to double the number of students. I'm going to go from 30 to 60, but then I'm going to move into a classroom that's twice the size. If I double the number of students, but I also double the size of the classroom, am I going to increase the frequency of my collisions? The answer to that is no. Okay, so this one's maybe a little bit confusing. The answer to that is no. You're not going to get more frequent collisions because you're expanding the size that the particles are in. So this has got no effect on rate. All right. But because you're starting with more particles, you are starting with more sulfuric acid, you will make more product. So when you're drawing this on a graph, I mean the rate should be the same. So I'm not drawing it steeper, but it does go higher on the y-axis because you're making more product. The next one, what happens if the reaction mixture was heated? So I'm talking about temperature. This one should be okay, but just remember that there's 2 distinct points that you're going to need to make here, and I've done this right down at the bottom. Okay, so I've got 20 degrees versus 40 degrees, okay? So I'm saying that at 20 degrees, I'm getting 100 collisions per second. I'm obviously just making up these numbers. And I'm saying that 20 out of 100 of these are successful. So most of them don't have enough energy, and when they collide, they just bounce back off each other. If you increase the temperature, okay, the particles will move faster, and therefore they are more likely to collide. So the first thing I'm expecting is that I get an increase in the frequency of the collisions. So maybe instead of having 100, I now have 200 collisions per second, okay? But the other thing that happens is because they've got more energy, more of them are likely to meet the activation energy, and more of those collisions will actually result in a reaction. So instead of having 20 out of the 100 successful, maybe now I've got 140 out of 200. So I've gone from a 20% success rate all the way up to a 70% success rate. So not only are those collisions happening more frequently, but more of them, a higher proportion of them are successful. Therefore, my rate is going to increase. Now, the important thing to notice, though, is even though these collisions are, the successful collisions are happening faster, let's just say you're trying to make 20 centimeters cubed of hydrogen gas, okay, and that's what you're going to end up making. Because you haven't added more reactants, even at 40 degrees, you're still going to make 20 centimeters cubed of hydrogen gas. And let's say that to make 20 centimeters cubed of hydrogen gas in total, you need 2,000 successful collisions. Again, I'm just totally making up numbers, all right? 2,000 successful collisions, okay? Those 2,000 successful collisions are going to happen a lot quicker because they're colliding more frequently and more of them are successful. So you're going to hit those, on this side, on the 40 degree side, you're going to hit that 2,000 much quicker, okay? But with the 20 degrees, you'll still end up hitting that 2,000 eventually. It'll take longer, but you'll end up hitting that 2,000 threshold eventually because you're making the same amount of product in both. So just do not say that you've got more collisions, you've got more frequent, they're happening faster, and you've got a higher percentage of them being successful, but you can't say more of them are successful. If you end up making the same amount of product, overall the same number of successful collisions will have occurred. So when you're talking about temperature, make two distinct points, okay? You are going to tell me that you've got more frequent collisions because the particles are moving faster. You're also going to say more particles reach the activation energy, so a higher percentage of the collisions are successful. What if you grind the magnesium into a fine powder? So magnesium is a solid. A piece of ribbon would be like a long thin strip of magnesium. If you grind that into a powder, maybe using a pestle and mortar, you are going to increase the surface area, and all of the atoms that were inside are now exposed to the sulfuric acid. So you are going to increase the rate because you've increased the surface area and more of the particles are available to react. Now if you had 2 grams of magnesium ribbon and you ground that up, you've still got 2 grams of powder. You're not increasing the amount of magnesium, therefore the amount of product that you're making should be the same, but the rate will be faster because you've increased the surface area. What does a catalyst do? This is the only time you shouldn't be talking about more frequent collisions. So a catalyst increases the rate by lowering the activation energy, and again that means a higher percentage of the collisions are successful. So if we look down here, I've got catalysts without and with. So let's say you've got 100 collisions per second. You will still have 100 collisions per second even if you've got a catalyst. It doesn't increase the frequency, but over here 20 out of 100 resulted in a reaction, and over here maybe 90 out of 100. If you drop that pass mark right down, more of the collisions will be successful and you're going to get 90%. I keep saying more collisions. A higher proportion of the collisions will be successful. Again, if you're making the same amount of product, and you are, overall the number of collisions will be exactly the same between the two, but because that percentage is higher on this side, you'll get to that magic number quicker, okay? So you're going to say blah blah blah, higher percentage of the collisions are successful. You're not going to say there are more successful collisions, you're going to say a higher percentage of the collisions are successful, but overall the number of successful collisions will be the same. Last one, explain the effect if it was carried out in 250 centimeters cubed beaker instead. This has no effect, okay? There are 5 things that affect rate: temperature, concentration, pressure if you've got gases, surface area if you've got a solid, and a catalyst. If I say catalyst, I can't remember it. But anyway, 5 things. The size of the flask does not affect the rate. They often put that into multiple choice questions as a distractor. Don't be fooled. Size of the flask doesn't affect the rate, so no effect on the rate. Right. If you've got any other questions about anything in the video, ask me. I mean, I'm assuming most of you will probably watch this the night before, so you won't have time to ask me questions, but if you have watched this in advance and you've got questions before your quiz, come and find me.